Hiya. So in this lecture, we're going to be talking about orientations of vector spaces. So let's kind of begin. So you've probably heard about orientations before. And this is basically like sometimes when we're talking about two bases having the same having the same orientation. If they obey like the right hand rule or a left hand rule or stuff like this, you might have learned this in physics. Alternatively, sometimes we might hear about something like a mirror image having the opposite orientation to its source. So like these kind of words like same orientation or opposite orientation, this is basically the kind of idea or the thing we're going to be looking at next in regards to vector spaces in particular. So we're going to try to like make more precise what we mean by orientation, if it's same, opposite, etc. We're going to try to like pin this down and kind of see what this does. So we're going to start off with two bases, B and C. So we need some kind of thing to compare, right? Two things have to be the same or opposite, so we need two things. So two different bases for the same vector space V. And we let T be the transition matrix from the basis B to the basis C. So T is basically the transition matrix from B to C. So what we're going to say is that B and C have the same orientation. So C has the same orientation as B. Well, what are we going to use? Here we're going to say that it's when this determinant, the determinant of the transition matrix, is greater than 0. And likewise, if we want to talk about something having an opposite orientation, we're going to say that the determinant of T is going to be less than 0. So here you might be like, well, what happens if the determinant is 0? Well, remember that the transition matrix, so a key part, is that remembering that the transition matrix between bases is non-degenerate. In other words, the determinant cannot be equal to 0. So in other words, these are basically the only two cases we have to worry about, and it doesn't really matter outside of that. So let's look at an example to kind of see where this kind of fits into everything. So let's start off with something super simple. We're going to start off with a line. So we're going to assume V here is a line. E here is the vector space. E is a line. So this is basically saying that it's a one-dimensional. That's what a line is, a one-dimensional vector space. So 1 dimensions, that's it. So if I look at any non-zero element of E, this spans the space. So anything that's non-zero, this is going to be the entire space, right? So one thing you can kind of think of this, if you really want, is like the real line. We have 0 here. And any kind of point I choose, like for example here, if I take this, the basis B here, B is equal to 2. Well, what is this going to refer to? This is going to refer to the 2 here. I guess we'll do 2 lines. 2, I guess I can just write these underneath. And if you think about it, any point on the line is some factor or scalar multiple of 2. So I can like scale this in any direction. So in particular, like for example, this point here, this would be lambda 2. So the only number we can't do this with is 0, right? Because 0 times anything is just always 0. So I can't do like scalar multiples of 0. So this only works with something non-zero. So in our example, we're going to have 3 bases that we're going to work with, B, C, and D. So B is just the number 2, C is the number -8, and D is the number 10. And the question we're basically asking, I can just scroll up here. The question is, which bases have the same orientations and which have the opposite orientation? So in other words, what we want to do is we want to calculate this transition matrix. So we want to look at this transition matrix here. We want to then look at its determinant, and that'll give us what we want. Okay, so what's the transition matrix from B to C? Well, this turns out to just be the, basically, how do I get from B to C? We multiply by -4. So B to C is equal to -4. Where is this -4 coming from? Well, that's because -8 is equal to -4 times 2, right? So the other way of kind of looking at this, if I look at some vector f1, this is equal to some number, lambda 1, times E1. And this lambda 1, remember, is going to be what our matrix is, right? This is our transition matrix. So this is basically what's happening. So our F1 is given by, right? This is our F1, and this is our E1. So if you think about this for a second, you're going to get a similar thing when we go to D. So if going from B to D, for example, this is just going to be 5, right? This is the transition matrix 5. Okay, so then what is the same and opposite orientations? Well, the determinants here are just the entries, right? So the determinant of BTC is equal to -4. Therefore, we have opposite orientations, right? Because the determinant is less than 0. So we have this condition here, less than 0. On the other hand, if I look at the other side, so if I look at the determinant of BTD, this is going to, D is equal to 5, and therefore they have the same orientation. Yeah. So in other words, B and C, B, D have same orientation, I can't spell, and C, that does not look like a good D. C has opposite orientation. Yeah, we can still see. Awesome. So let us look at one more example. Example number 2 for this. Let's look at something a little more complicated. And here we're going to look at something two-dimensional. So I'm going to have two different bases here. So here I have basis 1. Here I have basis 2. So here, remember, we can consider this as E1. This is E2. This is F1. This is F2. So what is... Here we need to figure out the transition matrix. So what is the transition matrix? Well, what do we have? We have that F1, right, is equal to E1 plus E2. E1 plus E2. So here you can kind of see this is E1, this is E2, right? Because we have the canonical basis here. And then F2, this is E1 minus E2. So our transition matrix here, remember we're doing columns. BC is equal to 1, 1, 1 minus 1. And the determinant for this, therefore the determinant of B, C, C is equal to -1 minus 1. So it's -2. Therefore, they have opposite. Therefore, they have opposite orientation. Yeah, so that's kind of nice. We will end this video here, and I'll see you next video to kind of see like how do we fit things into being opposite or the same. When are they, like, is that really it? Is there maybe some third option for orientation, or is it really just opposite and same orientations and we're kind of happy to go? So I will see you in the next video. Peace.